Hello everyone, this is Spencer Snowling from Hydromantis, and we'd like to thank you for coming in this afternoon or this morning or this evening, wherever it is that you may be joining us from. So today's webinar is going to be about using the GPSX hybrid unit process model, which is a combination of our suspended growth and our attached growth models and is used to do IFAS and MBBR modeling in GPSX. Okay, so I think we're going to get started right away. If you have any questions that you think of along the way, please feel free to type them into the questions box that you should see on your little dashboard there. And we're going to leave some time at the end to be able to answer any questions at that time. But if you think of something along the way, please feel free to drop it in there, and then we'll start answering when we get to the end. Okay, so this is myself, Spencer Snowling, Vice President of Business and Product Development, and I have with me today Hank Andre, Senior Process Engineer. Both Hank and I have longtime users of the IFAS model in GPSX and done several consulting projects with it, and so I invited Hank along for a little moral support today. So my plan is to discuss the hybrid model, just give you a little background on its history and its development, and then we're going to go through some of the details of the equations and the modeling approaches that are used in our biofilm models and specifically in the IFAS model. And then spend a little time about discussing about the important things you need to know when you want to set up a hybrid model for use as an IFAS or an MBBR system in GPSX. I'm going to run a quick demonstration, show you some of the interesting features of the model, and then talk a little bit about a case study or two that we've done here, and then leave some time for some final thoughts and some questions at the end. So the hybrid model, as we call it, is hybrid in the sense that it combines the suspended growth and the attached growth models of GPSX. And it was first introduced in version 4. We actually had it in-house for development for a couple of years prior to that. But so it's been around for about 10 years or more in GPSX. And the version that you are using today, excuse me, is a combination of our dual inlet plug flow tank object, as shown in this diagram here with the 2 inlets on the front, and our one-dimensional biofilm model that is present in some of the other biofilm objects in GPSX. So the biofilm model is roughly the same approach that we use across all of the attached growth models in GPSX, such as the trickling filter, the BAF, and the D-Night filter objects. However, when we're using it in an IFAS context, it's there to represent a biofilm surface that's either a fixed or a floating media in a plug flow bioreactor. You can set it to 1 tanks in series if you want to use it as a completely mixed system, or by default it's set to 4 reactors in series. So what we're doing in this case is we're looking at a total biofilm surface area that's in each one of the cells of our reactor. And we calculate that from a number of parameters in the model that you'll need to specify in terms of how it's being filled and what the physical properties of the specific media is. So, for example, we have that floating media that's sitting there in the tank. We take those irregularly shaped objects and we then convert them to one continuous media surface, which we apply our biofilm layers onto. So this is more or less the same approach that we use in all of our biofilm objects, and it allows us to reflect the different types of media by having different specific surface areas. So in the case of the model, this is sort of a hypothetical construct of how GPSX sees those biofilm layers. So we have the media side here on the left, and then there are sort of 5 what you could basically call reactors that represent the layers of the biofilm. Then there's a small liquid layer interface, and then in the case of our IFAS reactors, there's also the bulk liquid out here that represents the volume of all of the rest of the liquid in the tank, so out here with your mixed liquor and so on. So while that makes up our one-dimensional model in the sense that we have diffusion into those layers. So there's 4 processes going on at all times there, where we have diffusion of the soluble components from the liquid into the biofilm. And then once it's in that biofilm, it diffuses through all of those layers going towards the media surface. We have attachment and detachment of the solids on that interface. And then we have an internal exchange of solids within the biofilm. So if you have growth of new biomass inside that biofilm, it can grow up and push out into outer layers. And then on top of all of that, we of course have the biological reactions, just like you would have for all of our activated sludge models. They're going on in each one of those biofilm layers. And so what you can do is you can plot the gradient of the concentrations through those biofilm layers at any point when you're using your model, and I'm going to illustrate that when we get to our demonstration later on. So just to give you a graphical representation of what's happening, again, this is our media surface on the left and the biofilm in the middle, the 5 layers, and then our liquid on the right. So we have attachment and detachment of solids. So that's taking solids that are out here, attaching them onto this outer biofilm layer. We have a diffusion in and out as well. So your oxygen, your ammonia, and so on are being diffused into those layers. And once it's in, you can have diffusion within each layer from one layer to the next. And then the same sort of process for the solids exchange within those layers as well. So the next several slides are going to describe how those processes are modeled. Really what we're doing here for the diffusion from that liquid layer into that outermost first biofilm layer is using a KLA value and then taking the gradient of those concentrations. The KLA value is calculated from under our mass transport menu, the diffusion of the soluble components in water, and then we apply a reduction in diffusion from the biofilm. So we have a default value of 0.5 for that, and that seems to work well. It's not a number you have to make an adjustment to very often. So once that's got some of those soluble components into the first biofilm layer, you can then move internally as well, and we use a different equation there, sort of a second order situation here, where we're again using our diffusion coefficients and our reduction of diffusion in the biofilm layers. And then we're applying it across several layers all the way through into the innermost layer of the biofilm, the one that's closest to the media. The internal solids exchange is roughly the same concept as that internal diffusion, where we're looking at concentrations across several biofilm layers. And in that case, we have a separate parameter for doing that, the internal solids exchange rate, which you can find under the More button. And these parameters down here describe how fast that internal solids exchange happens between layers. Now lastly, attachment and detachment are done with 2 separate equations in GPSX. Our attachment from the liquid, that's attachment of solids from the liquid to that outermost biofilm layer, is a simple first order rate that's proportional to the concentration of those solids out there in the liquid. The detachment is a little more complex because it's the thing that's going to regulate the thickness of the biofilm. So we've got 2 or 3 different things going on here. We have a detachment rate that is proportional to the concentration of that biomass out there. And then we have, the concentration of the particulate component that's in that biofilm layer. So the attachment is proportional to the component concentration in the liquid, whereas the detachment is proportional to the amount that's in the actual biofilm layer. And then we multiply by this term on the right-hand side in the brackets here. And what it does is it adjusts this detachment to keep that growing out to the maximum biofilm thickness. But as that thickness reaches the maximum thickness layer, this increases the detachment so that it sort of regulates it, turns it up as required to never let the biofilm grow past the maximum biofilm thickness value. So that's how our detachment works to try and keep things in line. We then also multiply all of this factor by an anoxic condition, the anoxic shear reduction factor. So when you have anoxic conditions, when you feel that maybe there is not going to be as much detachment because you don't have as much vigorous mixing, you may not have those plastic media banging into each other quite as much, you could leave this at 1, or if you felt that shear was going to not be present in your tank, you may want to dial this down a little bit to reduce the amount of detachment in your biofilm. So what this then leaves us with is the image that I showed you earlier here, where we have all of these processes going on, and we are now modeling the concentration in each one of these biofilm layers. So these are treated somewhat like little completely mixed tanks in series that are connected hydraulically through all of these different processes. And then we convert them through a calculation where we convert the concentration to a thickness via the density and dry materials content of that biofilm. Those are parameters that you can adjust in the model. However, we generally find that the default values are fine. So what you end up with here, you may have different concentrations in these 5 layers. That gets converted to different biofilm thicknesses when you look at it from a thickness point of view. So the model is sort of doing this part, this interpretation here, to be able to understand modeling all the concentrations. But that maximum biofilm thickness detachment relationship that I mentioned is applied to this interpretation of the model. So it's doing all of these calculations simultaneously, but this is the one that's sort of the practical application. The reason we do that maximum biofilm thickness parameter is because it's one that people can intuitively understand and have a rough feeling for in their particular systems, and it allows us to sort of make the model more practical in the sense that we can use some values that people might have a good handle on for their plant in reality. Okay, so we have a few thoughts here on setting up that hybrid model. This is pretty much the same whether you're doing it as an IFAS system or an MBBR system. Most of the biofilm parameters that you'll find on these menus, they can be left at the default value. So you may see things like the dry materials content and the biofilm density and so on. Those types of things, most of those can be left the same. There are a few parameters, however, that you must change to be able to reflect the choice of a particular type of media. So that would be the media-specific surface area, for example. And there are a few other things, some of those rates that parameters that I showed you on the equations here in the previous few slides that could be adjusted as part of your calibration. However, most of the time you won't need to do that. So just to summarize quickly, the most important parameters that you should be looking at when you are setting up a GPSX model for IFAS or MBBR is, first of all, on our physical parameters input menu. If you get past the top part up here, which was the tank volumes and so on, the next part down relates to the media. So we're looking at the volume of the reactor that is filled by the media. So this is a fraction, 50% fill or 30% fill, whatever happens to be appropriate. We next have to fill in these 3 numbers here. These are the ones that are specific to the different types of media that are out there. The specific surface area is obviously a key parameter. That would make our overall amount of surface area to grow biofilm on different depending on what type of media value you've entered in here. The water displacement and density and so on is used in some of the other calculations to determine how much liquid is left over for IFAS systems. And, excuse me, another item that may or may not be of interest, it depends on the system, is this maximum biofilm thickness. This is the one that I mentioned that is going to regulate the amount of growth that can go out to your system. This generally is a parameter which, when I'm doing my jobs, I leave it the default to start with and then see how the calibration goes, and then we can possibly make some changes to it downstream. This is a parameter that we've had some experience with, which differs significantly or can differ significantly between municipal and industrial treatment systems. So biofilm thickness may be a relevant parameter in some industrial treatments, specifically if you have high rate treatment or a very large amount of substrate to work with, such as food waste treatment. Okay, so that was the physical setup menu where you're describing your tank and your media. So the mass transport menu, which is the next one on the list for that particular object, is where some of these other parameters that were involved in all of those equations that I illustrated earlier. This is where you'll find your reduction in diffusion and so on. So these biofilm calibration parameters are generally ones you don't need to change. So generally when I'm giving courses on how to calibrate our models, I recommend you leave all these at their default values to start with. If you do feel that you have evidence, or if you know your plant well and you know that shear is a real issue for you, this is the parameter, this mass transport menu is where you would come to make that change. Okay, so just a last few thoughts and tips on setting up that model. As with all activated sludge models in GPSX, influent characterization is very important. This is just as relevant for an IFAS or an MBBR system as anywhere else, and of course you are carrying some very high concentrations of substrate and inerts and other things in your biofilm, so this can be especially key in this type of a system. As mentioned earlier, maximum biofilm thickness sometimes is not relevant, but sometimes can be a limiting factor, as I mentioned, specifically in cases where you got a lot of growth happening from a lot of substrate available. Now, the nice thing is in this unit process object, you've got a lot of biofilm-specific model information that you can plot on graphs, in addition to the regular stuff that you would normally have from a plug flow tank. So there are a couple of other output variable menus, biofilm profiles and hybrid process rates, that are things that are specific to this type of a system, and they're very valuable in order to be able to plot them and understand what's going on in your biofilm. So I'm going to show you an example of that right now. I'm going to flip over to my desktop here and bring up GPSX. So this is our demonstration of the hybrid object that comes with GPSX. If you go to the sample layouts menu, you can find this under our IFAS /MBBR system. So this particular case here, this is set up as a flow through MBBR. You can see there is a recycle here, but right now I have that flow turned off. So this is not going to be carrying any mixed liquor. Really, it's just the flow through MBBR system. So let's solve that and run a one-day simulation. And you can see here our mixed liquor is fairly low. This is a relatively lightly loaded plant. And if I look at the information that we can get back here, we can see soluble substrates being used up, our ammonia is being removed, and lots of nitrate generated. So this is a fully nitrifying system here. So, but what I would point out is these four graphs here, these ones are showing the concentrations in the liquid as you go down the length of this plug flow system. Those are available in the place that you would normally expect to find them. Under the output variables menu, these state variables state variables in individual reactors. They are the liquid concentrations as it's moving down. But what you also have is the ability to do this type of graph here, where we're looking at the DO profile through the biofilm. So we can see in the outermost layer the concentration of oxygen is high, and then it reduces down as we go inside, and it's actually quite anoxic for this this particular tank. So this is the front end of that system. So it's using up a lot of the oxygen right on the front end of that system. So so you can plot those. Where you can find those is to go back to that same menu, pop up here to Biofilm Profiles, and you'll see we have created a profile for every one of the state variables. So you can see dissolved oxygen here. You could plot ammonia. You could plot the biomass profile. You could plot alkalinity, anything that you like. And here's the first tank, and then you just slide down second tank, third tank, and so on. So there's a very large amount of information for you to be able to plot here and get a feeling for what is really going on inside my biofilm, in addition to what's happening in the liquid tank as well. So one other thing I'd like to point out here as well, we've also created this other menu here, and we've spent a lot of time developing this over several versions of GPSX, is what we call our special hybrid rates menu. Hybrid process rates is the name of this menu. You can see here that we have some of the things you would normally expect to find in terms of OUR and nitrogen utilization rate and denitrification rate. This is for the liquid and biofilm together. But then we've also done some other interesting things here in terms of OUR per unit surface area of the biofilm. So the section at the top is more or less the liquid and biofilm together, and then this is biofilm only on the bottom. So that allows you to sort of distinguish what's happening, how much your biofilm is contributing to this particular system. So there's lots of information to be had, and you can do lots of interesting things. There is even the ability to let the media itself float around and change dynamically over time. I don't think those types of systems, that would be the kind that instead of hard plastic rings would have been more like sponges and so on. I don't think those systems are that popular anymore, but we still maintain that ability to do that. Okay, so Let's go back to our slides. Okay, I'm going to say a few words about a project, interesting project that I worked on in Groton, Connecticut. This was 3 years ago. I presented a paper on this at the WEF Biofilm Reactors Specialty Conference in Portland, Oregon in 2010. If you have an opportunity to get the proceedings from that, my paper is on there. Essentially, this was a small system in Connecticut that was converted to an IFAS. And I became involved when the vendor asked us to prepare a model of that plant so that the operations people could get a feeling for what their options were with respect to operating that plant. We felt that a model would give them an opportunity to familiarize themselves with what was going to happen in the plant under different situations. So this was a fairly small plant, 5 MGD. It's an MLE system. And their target was total nitrogen in their effluent of less than 7 milligrams per liter. So this is what the model looked like in GPSX. They had added IFAS to 2 of their 3 bioreactors, and they had the opportunity to split their mixed liquor across these 4 clarifiers. These were 2 new ones that were built at that same time. Their objective was to have the model so that they could take some time to look at what was going to happen when they took these 2 older clarifiers out of service to be repaired. So in this particular case, we didn't have to make much changes to the biological parameters at all in order to be able to do the calibration. It was, I must say, a relatively straightforward plant to model. We really, in this case, only had to change the influent characterization, which is common, and then make some changes to the clarification parameters in GPSX, and that basically brought all of our mixed liquor and everything else in line. So in this particular case, I was able to match a rough steady state calibration only, matched the mixed liquor, matched their effluent, BOD, and ammonia nitrate within the range of the data, within the variability of the data that they had available. So the interesting thing that the model was showing us, and I've seen this in some other systems as well, is you can take a look at that profile of the biomass and how it sits in that biofilm. So this is heterotrophs on the top and autotrophs on the bottom. This is liquid on this side. You can see here the autotrophs live more on the outside of that biofilm, and the heterotrophs live on the outside of the biofilm, and the autotrophs live somewhat more on the inside part. This actually was interesting when I presented at the Biofilm Conference in Portland, in the sense that there were some other papers from Technical University of Denmark that sort of illustrated some other laboratory experiments that kind of gave the same flavor to the distribution of the biomass within a biofilm. So once that was up and running, we got the operators to play with the model a little bit, and I helped them model a couple of different situations. We tried to see what was going to happen when we had peak flow with 2 clarifiers out of service and peak flow with 3 clarifiers out of service. And while everything else was relatively the same, they did have an increase in effluent solids when they took out 2 of them at the same, 2 of them at the same time. So basically, while I was there, they also wanted to investigate the use of supplemental carbon for denitrification. We implemented that into the model as well, showed them that it would take about 9 or 10 days to reach their new equilibrium, and provided them with a sensitivity analysis, which you can do as well, showing different levels of carbon addition and seeing what kind of effluent nitrate they were going to get and what level of total nitrogen would be involved. So that was a fairly useful thing for them, and they felt there was some value in having the model to be able to do that. I'd like to quickly point out that my colleague Rajiv Goel presented last fall at WEFTEX 2011 another excellent paper on our biofilm model, and specifically using it for an IFAS situation. And so if you haven't a chance to go to the proceedings for last year's WEFTEC, you can find that paper there. He had done quite a bit of work on looking at how the model reflects changes in biomass density throughout the year when the temperature and the loading is changing. And so that was another paper that has quite a bit more detail about our model as well. So a few final thoughts here in the last few minutes. Our hybrid model is fairly straightforward to set up, actually, compared to, I know if any of you have been to our past webinars. You know, the SBR is a little tricky, and the MBR has some features to it, but the hybrid model is not too bad to get set up and running. It does require some extra information, obviously, about the physical properties of the media that you're using, sometimes a little bit of extra calibration effort as well, but it's certainly one of the most popular GPSX unit process models. We find a lot of people are using it to model an existing activated sludge tank, and then they want to put some media in there to find out you know, how that system would look if we converted it to IFAS. So I will thank you all for coming today, and if you want to stick around for a few minutes, we're going to answer these questions. Otherwise, I'll wish you a good day, and thank you for joining us.
Thank you for watching this video. If you're interested in information on our other software products, such as CapNetworks for preliminary design and costing, ToxChem for industrial wastewater treatment modeling, or WattPro for drinking water treatment modeling, you can visit our website at www.hydromantis.com for further information.